Google's not being tech savvy. All right.
Teaches you how to use it.
Yeah. So in any case, what I have here is two 2-liter bottles side by side to show you one's going to react and one isn't. And we're going to see if this reaction is exothermic. You guys remember what exothermic means?
Yeah.
Okay, it means that something is giving off energy. We're going to learn today that giving off energy is a net change. There's energy that has to be absorbed also, and there's energy that's also released. Okay, so in this reaction, when we see any reaction that gives off energy, okay, it's because there's a net change, and I'll talk about that when we get to the lecture part. But in any case, overall energy is going to be released here. Let's see if we can see any evidence of that. I'm going to take some hydrogen peroxide. This is 30% hydrogen peroxide. Okay, you guys in stores have 3 or 6%. So I'm going to start with about 30% hydrogen peroxide. Okay, and now what I'm going to do is right now this is decomposing, okay, into oxygen gas, okay, and also water vapor. Hydrogen peroxide, you have to keep the bottle on tight because it'll become water over time. It's a mixture of water and H2O2. That's the molecule it's decomposing. So my friends in chemistry, right now it's breaking down into water vapor, okay, and O2. Bonds are being broken, okay, and also we're reforming new bonds. Now, I'm going to speed up the reaction with a catalyst, manganese dioxide. So it's happening now, but happening at a low rate. By putting a catalyst, I'm speeding it up, and we're going to see the effects of the decomposition and the exothermic reaction. So here we go. Remember the I Dream of Jeannie show that used to be on? Now what's happening to the bottle if you watch carefully?
Shrinking.
Yeah, look at its label. It's kind of like it was at a size 3 dress and now it's a size 0. Okay, if that makes any sense. This is now a tube top. Okay, I think we can do some more. It looks like to me that it's still working its magic. So let me add some more catalyst here. Okay, and we can see that that is oxygen vapor and water vapor being produced. And again, very exothermic because the bottle is shrinking. So they can tell that the heat is being released. Okay? All right. In fact, still like there's still some more. I think this catalyst here is not so great. Here we go. Now we're talking. And that's the decomposition, all right, of hydrogen peroxide into water vapor and oxygen. Very exothermic. You can see that clearly that the bottle to the right is much, much smaller. Okay? You can see that the label doesn't fit anymore. Lost too much weight. All right? And we'll stop there.
In this video, we're going to identify and state chemical equations for the decomposition of compounds. A decomposition reaction is simply a reaction in which substances are broken down. If we're to visualize what that means, what we can do is we can take, for example, a compound and break it down into its elements. It is actually the opposite of synthesis reactions, which were looked at before. In a synthesis reaction, we took A plus B and made the compound AB. Now we're just flipping that. We're starting with this compound and breaking it back down into its elements. Some examples here in terms of identifying them is if you see a compound being broken down into 2 elements, or it can also involve a complex compound being broken down into several simple substances. So what does that look like? Well, here we have a compound being broken down into the element oxygen and the element carbon. In the second example, we have vinegar being broken down into methane. So you can see here methane is CH4. It's not an element, it's still a compound, and CO2 is still a compound, but these 2 compounds are simpler than the original complex compound. And we can also think about it in the fact that usually you start out with something you only have one thing you start with, so we had 1 vinegar, and then you end up with more products. So here you end up with 2 substances. So 1 became 2. That gives you the idea that it's been broken down. So if it increases in numbers in terms of the substances you have, then that gives you an indication that it's also possibly a decomposition reaction. Now let's talk about how to do the chemical equations for these. So this is the process we go through. First we need to write each element separately. So let's start with an example here of ammonia. Ammonia is used in fertilizer, and so I know that it is actually a liquid, and if you didn't know that, you could look it up. So we start out by writing each element separately. So this is made of nitrogen and hydrogen. So I will start writing my chemical equation by having the arrow sign, and I'm going to have nitrogen and hydrogen. Now the second step is I need to think if I need to add any subscripts for the diatomic elements or the exceptions of phosphorus and sulfur. So I see, yes, nitrogen and hydrogen are both diatomic, so I need to add in their two subscripts. Their states, nitrogen and hydrogen, are both gases. Now that I've done that, I just need to balance. So I just need to check here. There's 1 nitrogen here, 2 here. That's no good, so I'm going to have to multiply that side by 2. And then after I do that, I'm going to have to check that everything is balanced. So let's see here. 2 nitrogen, 2 nitrogen, 2 times 3, 6 hydrogen on the left side, 3 times 2, 6 hydrogen on the right side. Now I'm correct. So let's do this for glucose. Glucose is made in photosynthesis. And if we're going to break it down into its elements, we start by writing out all the elements separately. It's made of carbon, hydrogen, and oxygen. And then I start to see, are any of those the exceptions up here? And I see, well, carbon is not an exception, so I just leave carbon alone. Hydrogen and oxygen are. And carbon's a solid. You can find that on the periodic table. It's like coal. Coal is carbon, and so that's solid. H2 and O2 are gases. Now I check my balancing. Well, I can see here I have 6 carbons on the left side. I only have 1 on this side, so I'm going to have to add 6 carbon. I have 12 hydrogen here, so I need 6 times 2 is just 12 hydrogen here. I have 6 oxygen here. 3 times 2 will give me 6. So now I'm all balanced with my decomposition reaction. Both of these examples are nonmetal and nonmetal, 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 nonmetal. So these are both covalent, but it's exactly the same for ionic compounds. So here's an ionic one, sodium chloride. We start off again by breaking it down into its elements. Sodium chloride is table salt, it's solid. We break it down into sodium and chlorine. Okay, and now we have to check, are any of those part of our exceptions? Well, sodium is not, so we leave it alone, but chlorine is, and it's a gas. And now we check to see if we need to balance. 1 sodium, 1 sodium. So far so good. 1 chlorine, 2 chlorine. No, that's no good. So I have to add 2 chlorine to this side. And see, there's a little bit of a mistake there. Let's just fix that up. You can actually tell if I go 2 sodium, now I only have 1 sodium here. So there's a bit of an error. So I need to fix that up really quickly. I can see here that it should be right there. 2 sodium. So now I have 2 on both sides. And that's how we do decomposition reactions.